Okay, so now there's kind of a broad classification of reactions called oxidation reduction reactions. And we'll see that many of those subtypes, like the combination, the single replacement, the combustion, many of those are also what are called oxidation reduction reactions. Or just for short, we call them redox, R-E-D-O-X reactions for short. So, oxidation reduction reactions are reactions where you have a transfer of electrons. So one substance is losing electrons and something else is gaining them. So we already kind of saw that with the ionic compounds, right? Where a metal would lose and become positive, and the non-metal would gain and become negative. But it does also happen actually even in molecular compounds. You just don't see it quite as clearly. But it's still transferring where one's reaching out and sharing one and things like that. So oxidation reduction. So oxidation is when you lose electrons. So if a substance is losing electrons, we call that oxidation. So I'm going to write that on the board. Lose electrons is oxidation. And when you gain electrons, that's called reduction. So if something is being reduced or undergoing reduction, we call that gaining electrons. The way that I always memorize this is lose electrons is oxidation, Leo. Gain electrons is reduction, Ger. Leo, the lion goes Ger. That's how I remember that. Leo, the lion goes Ger. So lose electrons is oxidation, gain electrons is reduction. I have to tell this little story that I always tell when I cover this. Several years ago back at Fresno City College, I had a couple of students in that class that were hearing impaired. So I had a sign language interpreter. They were interpreting everything that I was saying up here. I'm chatting away and I'm teaching this and they're, no sign language thing. So I get this part and they're going, they're going alongside and I say, okay, so Leo, the lion goes Ger, and they're going. So I just kept on saying that over and over and over and over. Make the interpreter go. We were all cracking up laughing, but anyway, yes, I was taking advantage of the interpreter from using them, but we were all found it quite humorous. So, Leo, Ger, lose electrons, oxidation, gain electrons, reduction. So, now again, we can't have one without the other. Just like we saw before, if one thing is losing electrons, something else has to be gaining, right? You can't have one without the other. Okay, so if one thing is oxidized, losing, well, something else has to take those electrons. They can't just go out and into space. They have to be something else that's willing to take them. Okay, so let me just look at a simple example here. So write this reaction down. Calcium plus sulfur goes to calcium sulfide. So let's consider what's happening to the two different elements. What's happening to the calcium? What's happening to the sulfur? So on the left side, we have calcium, just a metal, so it's not charged. It's just a metal, so it's 0. And then it goes on the right side, well, now it's in a compound, right? So calcium's in group 2, so it goes to calcium 2+. Right? So that means, if it went from 0 to 2+, well, that means it must have lost negatives, right? If it went from 0 to being positive, it must have lost 2 negatives. See that? Does that make sense? If something goes from neutral to positive, well, it must have lost negatives, right? Somebody, no? If you gained a negative, it would have become negative, right? But it lost negative, so it becomes positive, right? Okay, so calcium apparently lost electrons. So that's oxidation. Or you could say calcium was oxidized. Now how about sulfur? Well, sulfur on the left side, just by itself, so it's neutral. But on the right side, it's sulfide. So sulfide is 2 away from the noble gases, so it's 2 negative. So if it went from 0 to 2 negative, it must have gained some negatives, right? Because it went from 0 to become negative, it must have gained some negatives, right? Oh, so sulfur then gained electrons. It was reduced. Ger, gained electrons reduction. Okay, that's pretty much all there is to it. So we're going to look at the charges and figure it out. So again, if it's by itself, you know it's 0. If it's in a compound, now you know how to figure it out because you know how to do those charges in compounds. Okay? Now, technically, oh yeah, go ahead, sorry.
For the calcium, the oxidation, should it be minus 2 electrons at the end, or is it supposed to be?
Well, calcium lost 2 electrons, right? So it became calcium 2 plus, but it lost. It also made those 2 electrons because they went because it was calcium with the electrons here, and then it lost the electrons, so it's showing them separately here. Here it's saying, oh, the sulfur gained the electron and came together to make this kind of a thing. Yeah, sorry for the confusion. Okay, so remember way back I told you charges have to be written like 2 plus, not plus 2? Because I said back then, plus 2 is actually what's called an oxidation number. So technically, I would say on this, the charge is 2 plus, but the oxidation number, we'll actually write plus 2. Or here it was neutral, so the charge is 0, the oxidation number is 0. So technically, you can say the oxidation number is minus 2 on that. So just write it a little differently. And now we won't do, though, very advanced cases in this class. You can come back in 110 and we'll show you all kinds of more advanced ones. But
So the metals, are going to lose electrons, and the metals, and the non-metals are going to lose them?
yes, if they're ionic compounds, yes, that's true. That is true. But you can also have those molecular compounds, and they can gain and lose too. But yes, but the point is that one always loses, one always gains. That's true.
How will we know
Well, we'll kind of try a few here, and we'll see. Again, we're pretty much going to do just real simple ones, and in this class. So I think most examples we're going to do are metals and non-metals. So I think it'll be pretty clear. So let's look at your handouts. Pull out your Chapter 6 handout. We're all the way down to number 4. So let's just do an element by itself first, and then we'll do some whole reactions together and figure it out. So 10 neutral goes to 10-4. Is that oxidation? It lost electrons, or is that reduction? It gained electrons. So going from 0 to 4 plus, did it gain negatives or did it lose negatives? It went from 0 to 4 plus. Did it become more negative or less negative? It became less negative. It lost electrons. You can see it. It lost them because they're on the right side now, right? So that is, if it lost electrons, that's oxidation. So we would say that's oxidation. So, or you could say 10 was oxidized, you might say. But 10 underwent oxidation. Okay. Iron 3 plus goes to iron 2 plus. So did that gain a negative or lose a negative? It went from 3 plus down to 2 plus. It must have gained a negative, right? Right, it went lower. And you see right there, it gained negative plus a negative, plus an electron. Right? So it gained an electron, so that means it is reduction. So iron 3 was reduced to iron 2. Okay, chlorine neutral goes to chlorine negative. So did it lose negatives or did it gain negatives? It went from 0 to negative. It must have gained negatives, right? It must have gained electron because it became negative. And you see right there, plus 2 electrons. So if it gained, that's also what? Reduction. Okay, so chlorine was reduced to chloride. It's reduction. Okay, let's try it here in a little reaction together here. So, magnesium plus 2 hydrogen ions goes to magnesium ion plus hydrogen. So let's look here. So let's figure up the oxidation states, which is the same as the charge on these elements and ions. So what's the oxidation state on magnesium just by itself over here on the left-hand side? It's just 0, right? Okay. What's the oxidation state on the H+? Just same as the charge, right? So plus 1. How about the magnesium 2+? Plus 2. And the hydrogen is by itself now. What's the oxidation state? 0. All by itself, element by itself, just 0. So magnesium went from 0 to +2, right? Hydrogen went from +1 to 0. You see that? Right? Okay, so magnesium. Magnesium went from 0 to +2. Did it lose negatives or gain negatives? It lost some negatives, right? So if it lost negatives, that means magnesium was what? Oxidized. Underwent oxidation, yes. Hydrogen went from +1 to 0. See that? So does that mean it gained electrons or lost electrons? From +1 down to 0, it must have picked up some negatives, right? It must have picked up some negatives. Yes, so if it gained them, that means it was reduced. So just a reminder, you can never have both being oxidized or both being reduced, right? So if that happens, you probably made a mistake somewhere, because if one thing's being oxidized, something else has to be reduced. Okay, let's try this next one here. So we have aluminum plus bromine goes to aluminum bromide. So what's aluminum metal all by itself? What's the oxidation state? 0. Bromine all by itself? 0. How about aluminum bromide? What's aluminum now here in this compound as an ion? What's aluminum's charge normally in a compound?
Plus 1.
Aluminum is aluminum. What is it? 3 plus. So its oxidation state, I would say, is +3. How about bromide? Yeah. So the charge is 1 negative, so -1 is the oxidation state. Okay, well, let's write a couple little arrows here. So aluminum went from 0 to +3. Bromine went from 0 to -1. So, which was oxidized, which was reduced? Which one gained electrons and became more negative? Which one lost electrons and became more positive? Bromine gained electrons, right, reduced, right? Perfect. Because bromine went from 0 down to -1, right? So it gained some electrons. And obviously the other one, yeah, go ahead.
So since it's 2 aluminum and then 2 bromide, 3, that 2 in front doesn't affect its charge or anything? Does that make it +6?
It doesn't affect the oxidation state. Each bromine is still 0. Each bromine is still -1. Yeah. Okay, and aluminum obviously then was oxidized because it went from 0. It got more positive, so it must have lost some negatives to become more positive. So we said that was oxidized. Okay, your turn. Try the next one. Oxygen plus iron goes to iron 3 oxide. Oxygen plus iron goes to iron 3 oxide. Okay, ask your neighbor what they think. See if they agree with you. Find somebody across from you, next to you, wherever. What was oxidized? What was reduced? Okay, so you're going to name this. How would you name this? Pardon? Yeah. Charge. How would you name this? How would you name this? If I asked you to name this, how would you name it? Iron what? Iron's in the middle, so it means you're on the middle. Iron one, right? Oxide minus 2. How many of them are there? 3 is 3 times 1 is 2. 6 minus. These have to be 6 plus. There's 2 of them, so each has to be what? 2 times 1 is 6. Iron. 0 plus 3, 0 minus 1. Okay, so you and your neighbor agree? Unless you're not playing along. Okay, let's figure out the oxidation state, which again is the same as the charges for these. Neutral, so 0. Neutral, so 0. Okay, this is, we know oxygen is minus 2. Same as its charge. Put that 2 a little bigger. So there's 3 of those. That's minus 6. So this must be plus 6. There's 2 of them, so each one must be plus 3. So we had oxygen went from 0 to minus 2. And we had iron went from 0 to plus 3. So which one was oxidized? Iron, right? Iron. Oxidized means it lost negatives. It became more positive. So which one was reduced? Well, obviously the other one. Oxygen was reduced because it went from 0 to negative 2, right? So it became negative. It must have picked up some negatives. How do we do? Okay. Okay, we're going to spend the rest of the chapter, the next 3 hours probably, talking about the mole and stuff. So this is the third and last really big thing you absolutely have to know to pass chemistry. First was unit conversions. Second one was naming. If you can't do naming, you are so screwed, I cannot even tell you. And then the next one is this, the mole. So I've been saying that for 3 weeks. It is a language for chemistry. And if you can't speak the language, there's no way you can do the next 6 chapters. They're just absolutely freaking impossible. So hopefully you've used your break wisely, because we'll see on our quiz here in a little bit. So, the mole. So, atoms are super, super tiny. For example, one hydrogen atom only weighs 1.673 times 10 to the negative 24th. Okay, so these balances here, which are really expensive and very precise, they will give you 4 decimal places. To read all of that, you would need 28 decimal places. So you would need a crazy precise balance. Plus, of course, the atoms are so small you can never grab just one and weigh them out, right? So because they're so freakishly tiny, you're always dealing with bazillions and billions and trillions of them. Even if you only have 1 gram, it's bazillions and trillions of them at a time. So we need some number then we can use. So that number we use is called the mole. And a mole is 6.022 times 10 to the 23rd, whatever it is you are counting up. So just like a dozen is 12 whatever it is, a mole is 6.022 times 10 to the 23rd, whatever it is. And the abbreviation for the mole is MOL. Saves you one whole letter. Isn't that a great abbreviation? That's awesome. So, this is a really big number because we need to talk about lots and lots of them, even like a single gram or something. So, that is a very odd number. Why is it that really odd number? Well, that number is called Avogadro's number. Avogadro's number. Name for this sexy Italian guy here in the corner. Amedeo Avogadro. Avogadro. So that's called Avogadro's number. So 1 mole of something is Avogadro's number of that, whatever that thing is. And I remember when I first moved to California back about 10 years ago or so, I went to Trader Joe's and they had this guacamole. I think they still have it. It's the guacamole, and it's called Avocado's number. And look, it even has this picture right there. So now you know the little joke there. Avogadro's number, Avocado's number, guacamole. I thought that was very funny. So, where does that weird number come from? Well, it is the exact number of particles in 12 grams of carbon-12. So let me just rewind here a little bit. Remember, we talked about in nature, an element might be made up of multiple different isotopes. So, for example, carbon is not. So carbon. Not all carbon is the same. Some carbon is carbon-12. Some carbon is carbon-13. So if you had 12 grams of carbon-12, and you counted up all the particles that were in 12 grams of carbon-12, it would be Avogadro's number. So that's where that number comes from. So why do they pick carbon-12, though? I mean, why was that chosen? Well, the whole table, all of the masses on the table are based around carbon-12. So you know I mentioned this unit before called the AMU, right? It's a way of measuring really small things. Well, that's also based off carbon-12. Because carbon-12 has been defined to be exactly 12 AMUs. So 1 AMU is a 12th of a carbon-12. So everything on the table, all of those masses, everything is based off carbon-12. So now the mole is based off carbon-12. So now it's not, so if 1 carbon-12 is 12 AMU, how many carbon-12s are 12 grams? Oh, 6.022 times 10 to the 23rd of them is 12 grams. So that was where that kind of came from. Okay, so that's called Avogadro's number. Now, the other kind of offshoot of this, since it's all based around carbon-12, the same way that all of these masses here, right, the mass you have on your table underneath hydrogen, right? It says hydrogen on your table. If you have it there, if you don't, pull out your periodic table. Hydrogen says 1.01 under it. Well, yes, I told you one hydrogen has an average mass of 1.01 AMU. But 1 mole of hydrogen has an average mass of 1.01 grams. So it works in AMU for individual particles, and it works in the real world, kind of macroscopic world, in grams for a mole of them. So, for example, let's find there on your table oxygen. So 1 single oxygen weighs 16.00 AMU. But a mole, or 6.022 times 10 to the 23rd oxygens, weighs 16.00 grams. Are you with me? So that number works for individual atoms in AMUs, or for a mole of them in grams. Okay, how about sodium? Find sodium. What's the mass of sodium on your table? 22.99. So a single sodium atom weighs 22.99 AMU. But a mole of sodium atoms, or 6.022 times the 23rd sodium atoms, weighs 22.99 grams. Are you with me? So it's very handy. So yes, it works for the submicroscopic scale as well as the real-world macroscopic scale. Okay, so this is a huge number. I cannot quite show you how big this number is, but I will just write the number out if I even can, just to kind of give you an idea how big it is. So let me see here. Just made it. There you go. That is a mole. So think about that for a second. 1 gram of hydrogen. A gram of something is nothing, right? I mean, a gram weighs, it's literally like nothing. It just weighs almost nothing. 1 gram, though, has that many hydrogen atoms in it. So you weigh out a gram of hydrogen, it's got that many. So it's not, so here's 1,000, a million, a billion, a trillion, a zillion. I don't even know what these are. It's so big. It's tons of them. It's crazy. So if you had, I think it's 12 pennies, 12 pennies in your hand. 12 pennies. So I'll just draw 12 pennies. That's actually a little too big for pennies, isn't it? Pennies are smaller. Draw 12 pennies. Okay, if I had 12 pennies and they were pure copper, just to make it easy, well, 12 pennies is about the mass of copper on the periodic table, 63 or so. So 12 pennies in your hand is about 1 mole of copper atoms. Does that make sense? So if the pennies were pure copper, you'd be holding in your hand 1 mole. So think about it. So in your hand, you're holding that many particles in your hand. Now again, this is a huge number, so I want to kind of try to show you how big a number that is. So I have a few analogies here I found. One says, let's say we found around town here 10,000 people and had them then help us try to count out that number. And they were each counting it 100 atoms per minute. So they're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They would take those 10,000 people, counting the 100 of the atoms a minute, over 1 trillion years before they could count the atoms in your pennies one time. 10,000 people over 1 trillion years to count the atoms just one time, all the atoms in your pennies, or the atoms in 1 gram of hydrogen. Let's say we got a computer and went crazy, and the computer's going gangbusters, and it's counting them 10 million a second. Still take it over 2 billion years to count the atoms just one time in your pennies, or in 1 gram of hydrogen, because it is a huge number, because because atoms are really, really tiny, right? Okay, here's another mind-blowing one, at least to me. Let's say the particles here then in your pennies, they all grew in size to just as big as marbles. Okay, so not as big as marbles. Well, there's so many of them that they're all marble size suddenly, it would cover the entire planet 50 miles deep in marbles. The entire planet Earth is going to be covered 50 miles deep in marbles. Yet you're holding that many particles in your hand because they're so freakishly small. Isn't that weird to think about? They are super, super tiny. Okay, the last analogy I have. Okay, so let's say you have a typical glass of water. Okay, so 1 glass of water is actually about 10 moles. Okay, so 10 moles. Well, the number of the particles you have in your glass of water, there's more particles in your glass of water than there are all the grains of sand in the Sahara Desert covering North Africa. So you have more particles in your hand than you do all the grains of sand covering the largest desert on the planet. Isn't that crazy to think about? You're holding that many particles in your hand because they are freakishly small. They are super tiny. Atoms are super, super tiny. So we need this giant number, Avogadro's number, even to deal with a gram of something, okay? Okay, so, but again, remember, that number can be 1 mole of whatever you want to convert, right? It could be atoms, it could be molecules, it could be ions, it could be formula units, but it could be puppies or donuts or plants or whatever you want to count. Doesn't matter, anything. So just like a dozen is 12 whatever particles, a mole is 6.022 times 10 to the 23rd, whatever you're counting. Okay? Okay, so mole is our new friend here. So whenever we want to go from moles to some kind of particles, I encourage you to write this little thing down. We're going to use our new friend, Avogadro's number. 6.022 times 10 to the 23rd. So what are the particles? Well, normally in chemistry, we're looking at maybe it's atoms. If it's a molecular compound, the smallest piece is called a molecule. So maybe it's molecules. If it's an ionic compound, what's the smallest piece called? Remember? It's a weird name. Starts with an F. Come on. Think. Smallest piece of a molecular compound is a molecule. Smallest piece of an ionic compound is a formula unit. Formula units. Man, somebody got that in my class yesterday. I'm so disappointed. Or maybe it's just individual ions or something. Whatever it is, any kind of particles like that, okay? Okay, so go from moles to particles or particles to moles. We're going to use our new friend Avogadro's number. Yes?
I'm still kind of confused on this grams per mole.
Okay. Okay, we'll get there in a second. So hold on a second, maybe it'll make sense. Okay, so let's just try a couple examples here. So how many atoms, how many particles would be in 42.67 moles of copper? Moles of copper. Well, we know 1 mole of anything is Avogadro's number of that, right? Are you with me? 1 mole of anything is 6.022 times the 23rd, whatever that thing is. So 1 mole of copper would be 6.022 times the 23rd pieces of copper. What's the smallest piece of copper? Atom. Small piece of copper is an atom. So if I have moles to start with, I've got to have moles in the bottom of my conversion factor, which means Avogadro's number must go on top. So 1 mole is Avogadro's number. The only question is, do I want moles on top or moles on the bottom? In this case, I'm starting with moles, so I need moles to cancel, so I'd put it on the bottom. So just the same as any other unit conversion we've done. So now moles cancels, bloop, bloop, and we're left with that. So why don't you just pull out your scientific calculator, just make sure you remember how to use that exponent key and everything. Try it out here. So we'll do a few of these, and then we'll do a few of these with molar mass, Aaron, and we'll show how that works. Okay, everybody get that on their calculator? Remember, use the exponent key. Don't put a multiplication with the exponent. Just 6.022 exponent 23, not times exponent, else you'll get some wacky stuff here in a little bit. Awesome. Okay, how about the reverse? Now they said how many moles are in 8.46 times 10 to the 24th atoms of silver. So now they gave me particles over here, and they want me to go to moles. So I'm going to use Avogadro's number to go from particles to moles. So I start with what I want. Oh, so anytime you see particles, anytime you see atoms or formula units or molecules, or you think, oh, Avogadro's number. I've got to use Avogadro's number. The question is, does Avogadro's number go on top and moles on bottom, or vice versa? Mole on top, Avogadro's number on bottom. Which one is it going to be here? Avogadro's number goes where? On the bottom, because the mole would have to go on the top. So 1 mole is that many particles. Right? So the particles of the atoms cancels. Right? If that was flipped, now atoms wouldn't cancel, right? So I got particles to start with. I got to have the particles, the Avogadro's number, on the bottom. So again, same as any other conversion. You've done lots of these with meters and kilograms and things. Now we're just using a new little conversion, Avogadro's number. Okay, so try that one on your calculator. So here's where the exponent key will really serve you if you use it. If you don't use it right, you're going to get big, crazy, ginormous numbers, and you should get a small number. Yeah, you should get about 14. If you're getting like 10 to the 20-something or 40-something, you are not using your exponent key, right? You're still putting in an extra multiplication symbol or something. So 8.46 exponent 24 divided by 6.022 exponent 23. Okay, everybody get that? Guess no one's yelling at me, so I'll assume so. Okay, let's try your handout. So get out your handout there. How many formula units are in 15.2? Yes.
Sorry, for the last time, I was wondering why you don't have one decimal point for significant figures.
Let's see, it should have. 8.46 is only 3. 6.022 is 4. So it's 3 sig figs. Okay, how many formula units are in 15.2 moles of sodium chloride? So 15.2 moles. What's sodium chloride's formula? What's sodium's charge? What's chloride's charge? Figure it out. What's sodium chloride? NaCl, right? Na is plus, chloride's minus. Okay, so let's just look here together. I see this term, formula units, and I immediately think, that is a kind of particle. Whenever I see particles, I immediately think, I know what I got to use. I got to use Avogadro's number. So we're going to do a lot of these word problems, and it's really important to kind of pick out the clues here. Oh, formula units. Oh, that's a kind of particle. Ding, ding, ding. Avogadro's number. So let's look here. So I want to turn a mole into formula units. So will Avogadro's number go on top or bottom? Top, because the mole has to go on the bottom for it to cancel, right? So 1 mole of NaCl is how many NaCl's? Oh, 6.022 times 10 to the 23rd pieces of NaCl. And a piece of NaCl, it's an ionic compound, so it's called a formula unit. And I have no good abbreviation for formula units. I could write FU, but that just seems wrong. So I'm just going to write form units. So try that out in your calculator. 15.2 is 3 sig figs. 6.022 is 4 sig figs. We'll have 3 sig figs. So what's the answer? That'll be a big number. Why don't you get a number, Odalise? 9.15 times 10 to the 24th. Sounds good. Anybody else get that? 10 to the 24th. Whoops, that was really messy. And my units are formula units. Okay, so let me give you a little tip here. When you're writing these, make sure you don't just write 1 mole of something. Always write what the mole is, because here in a little bit we're going to have different kinds of moles, and you want to know which kind of moles cancel what kind of moles. So I'm just saying, don't write 1 mole write 1 mole NaCl. Does that make sense? Write 15.2 moles NaCl, and that'll save you. So I'm just telling you right now, get in the good habit here, because here in about 20 minutes, we need to know, moles of what? So some moles will cancel, other moles won't cancel. Okay, just giving you a warning here. Okay. Let's try this one. 9.14 times 10 to the 28th atoms. Oh, ding, ding, ding. I see the word atoms. That's a kind of particle. So I immediately know I'm going to have to use what? Avogadro's number. Okay. Is how many moles? So let's write down what I know. 9.14 times 10 to the 28th atoms. I could put atoms of what it is, I guess. Cobalt or cobalt atoms. Okay, I want to turn those particles into moles. Oh, particles into moles, Avogadro's number. Now I want to get moles out at the end. So will Avogadro's number go on top or bottom on this one? Okay, I need to get moles out on top. So Avogadro's number has to go on the bottom, yes. And again, don't just write mole, write mole of whatever it is, mole of cobalt in this case. Okay, so let's punch that in our calculator. Try it out, see what you get. Should get a, I don't know, roughly 10 to the 5th or something. It's going to be, looks like. It's 28 or 23. Okay, what is it? Anybody get an answer? Get an answer? There's you and knees. We lost some places. Did you put in 10 to the 25th? 10 to the Okay, yeah, exponent 28. All right. There we go.
Oh.
1.52 times 10 to the 5th. Awesome. And what's the units? Moles of cobalt. Moles of cobalt. 3 sig figs, 4 sig figs. The answer is 3 sig figs. Okay, your turn. How many eggs would be in 8.11 times 10 to the 6 moles of eggs? Because again, it can be anything. It doesn't have to be atoms. It can be any individual piece of something. Okay, ask your neighbor what they get. How many eggs would be in 8.11 million moles of eggs? We've got a lot of eggs. Cover the planet hundreds of miles deep in eggs. Okay, did you get a giant number? If you got a giant number. Okay, let's see what our giant number is here. So, 8.11 times 10 to the 6th moles of eggs. So 1 mole of eggs is Avogadro's number on top, 6.022 times 10 to the 23rd eggs. So what's the answer? Ten to the 30th. Again, that's a whole lot of eggs. I'm sure it would cover the planet 1,000 miles deep or something crazy, probably. It's a lot of eggs. Okay, so that's the first part. That's taking the moles into particles. But we don't really use moles when you're weighing things out. Weigh things out in grams. So I told you earlier that those masses on your periodic table, that is the mass of a single one of those elements, or it's the mass in grams of a mole of those elements. So for example, my table here, you see, one hydrogen weighs 1.001 AMU. But a mole of hydrogen weighs 1.01 grams. So 6.022 times 10 to the 23rd hydrogens weighs 1.01 grams. So one single magnesium atom weighs 24.31 AMUs. So that's called the atomic mass, the mass of an atom, atomic mass. How about if I had a whole mole of magnesiums? That would weigh 24.31, but now grams. So we call that the molar mass. That's the mass of a mole. So, I'm going back to my little flow chart here, so I'll just extend it here and take the moles. If I want to go to mass, moles to mass, it's right there in the name. We use the molar mass. And that's right off the periodic table. And it's grams per mole, the mass of a mole. So 1 sodium weighs 22.99 AMU. 1 mole of sodium weighs 22.99 grams. So the question is, though, how do we find the molar mass of a compound? Let's say it's not just a single atom. Let's say it's sodium chloride or barium chloride, and we've got multiple atoms. Works the exact same way. It's pretty straightforward. Let's say I want to know the molar mass of barium chloride. Barium chloride. Well, barium chloride's formula, you know, at least I pray you know of barium chloride, is BaCl2. 1 barium, 2 chlorines. So you just add up on your table, find the mass of 1 barium on your table, plus the mass of 2 chlorines. That's the molar mass of barium chloride. So you find barium on your table, it's 137.33, right? And you find chlorine, there's 2 of those, so 2 times its mass, which is 35.45. And you add them together, and 208.23. So that means a single barium chloride would be 208.23 AMUs, but a mole of barium chloride is 208.23 grams. So we just add up all of the masses for every element in that compound. Just add them up. Okay, let's try a couple here together. So, okay, if you haven't yet, pull that periodic table. We're going to use that a lot. Okay, let's just try a few on your handout. So get out your handout. Let's find the mass of NH4Cl. So NH4Cl, I'm going to add up all the elements in there. So I have 1 nitrogen, right? I have 4 hydrogens, and I have 1 chlorine. So what's the mass of nitrogen? 14.01, I think. What's the mass of each hydrogen? 1.01. Whoops. Try that again. So 4 times 1.01, so that'd be 4.04. And then 1 chlorine. Each chlorine is 35.45. I just add that all together. All right, add the nitrogen, the 4 hydrogens, the chlorine on your calculator. .50, I think. Grams per mole. Or AMU if you're dealing with just a single one. Yeah, question.
Just nitrogen would be 14.01 AMUs.
If it was just 1 nitrogen, 14.01 AMUs, or a mole of nitrogen would be 14.01 grams. Yeah. Okay, let's try calcium acetate together here. So, we got a lot of numbers and some parentheses. So, how many calciums do I have? 1 calcium. That's the easy one. How many carbons do I have? 4, right? 2 times 2. Right, because there's the parentheses. So here's 2 and here's times 2, right? How many hydrogens do I have? 6 hydrogens. And how many oxygens? Okay, so there you go. So add these all up. So 1 times the mass of calcium which I think is 40.08. 4 times carbon, which is 12.01. 6 times each hydrogen, 1.01. 4 times each oxygen, 16.00, right? Just add it all up here. $158.18. So what you got? Okay, ask me questions. Everybody sees where those numbers come from, right? Just right off the periodic table. We just add them right up. Okay, I think it's pretty straightforward. Why don't you jump down? Let's try the last one. Aluminum sulfate. Can't quite see it. Al2SO4 3. Okay. What's the molar mass of aluminum sulfate?
Just this thing.
What's the molar mass of aluminum sulfate? How many aluminums, how many sulfurs, how many oxygens? Just punch in your calculator. Okay, what'd you get for the mass of aluminum sulfate? I'm sorry, a little louder, I couldn't hear you.
Oh, 342.17.
342.17, anybody else? Okay, good. Okay, that makes sense. Okay, so let's put this all together here. So now let's use it. Let's use that grams per mole to convert grams into moles, or moles into mass. So, I can turn mass into moles with that, right? Or moles into mass, either way, because I have the units right there. So let's say I had, what is the mass in grams of 4.82 moles of silver phosphate? So here again, this is why you have to know how to name things, else you can't find the formula, then you can't find the molar mass, then you can't find the mass, and you are out of luck, I will say it nicely. So, hopefully we know how to name this. So, somebody wow me here. Whoops, I didn't hit the wrong button there. What is the formula for silver phosphate? So, let's figure it up real quick. What's silver? Ag what? What's the charge? 1 plus. What's phosphate? PO 4 3 negative. You've only had 3.5 weeks to learn those by now. 10 things. So, what's silver phosphate? Ag3PO4. Okay, add it up. Add up Ag3PO4. Get your periodic table, grab your calculator. 3 silvers, a phosphorus, 4 oxygens. Okay, what's the molar mass of silver phosphate? Anybody get a number yet?
1858.
That's what I got. That's what I got. 41858. Okay, so let's use that. So let's write down, what do I know? I know 4.82 moles. And again, always write down what the moles are of. Moles, silver phosphate. Okay. But I don't want moles. The question says, what is the mass in grams? Yes, mass in grams. So here's another little hint. Whenever you see mass in grams now, you should be thinking, oh, mass, what I got to use? Molar mass. Whenever I see mass, I'm thinking molar mass. Whenever I see atoms, molecules, formula units, I'm thinking Avogadro's number. So, where's the moles go? Where's the grams go on this? Moles got to go on the bottom, right? So grams goes on top. So it's 418.38 grams per mole of silver phosphate, right?
5.8.
Oh, 5.8, sorry. So 3 sig figs and 5 sig figs, going to be 3 sig figs. All right, work this out. What did I get here? 2.02 times 10 to the third grams. Okay.
Would you just leave it as grams, or would you leave it grams?
Moles canceled.
We'll cancel
Right, the moles canceled because the initial moles was no, it's grams per mole.
But when it comes like that,
Where did this mole come from? It's right here. It's grams/mole, grams per mole. There is no mole there on top.
so we're
See, this is grams over mole. So we did grams over mole.
okay.
Okay, let's try that. Let's get this. This one's too easy. Let's do the next one. Let's do this one. How many moles are in 692 grams of iron 2 phosphate?
Oh.
So let's just look at our hints here again. I see moles and I see grams. Whenever you see mass in these problems, you should be thinking molar mass. Oh, I got to use the molar mass. So, first problem, first obstacle, what is iron 2 phosphate? So figure out, what is iron 2? What's iron 2 mean? Fe2 plus, yes. What's phosphate? PO3, 3 negative. So what would iron 2 phosphate be? What? What's the formula? Fe3, parentheses, PO3, parentheses 2. There you go. Okay, so add that up. Add up 3 irons, 2 phosphorus, 6 oxygens. Anybody get a mass yet? 325.49. Anybody else? Let's see what I got. Yep, that's what I got. Okay. So let's try this now. How many moles are in 692 grams of Fe3 parenthesis PO3 parenthesis 2? Okay. So I have the conversion right there from grams to moles. Right, that's what the molar mass is. But now I'm in grams, so the grams has to go on the bottom, right? Which means the moles has to go on top. So 325.49. Try that again. Grams on the bottom. So the mole, don't forget to write what the mole is of, must go on top. So grams cancels, now we got moles, so I'm ready to work this out. Let's see what I got. 2.13 moles is what I got. Okay. Let's try a few. So, what is the mass in grams? These ones here on your handout, so you can get out your handout. What's the mass in grams of 51.2 moles of trichlorine godmother fluoride? No fluoride. 51.2 moles. What's trichlorine? 3 chlorines. What's nona fluoride? 9 fluorines. Good. Okay, so it's asking me for what is the mass. So whenever I see mass, oh, I got to use molar mass. I will say that probably 50 times in the next couple hours. It's so important. Whenever you see mass, oh, use molar mass. So, find the molar mass of trichlorine nona fluoride. Add up 3 chlorines plus 9 fluorines. Let's try it out here. Yeah.
So if we write it, you would write it just like that because technically, like, if we write it other ways, like we want to break it down to the smallest, right?
I want to break it down to the smallest.
Yeah, so like with 3 and 9, you could like break that down further. So it'd be like CL.
If it was an ionic compound, you reduce it down to the lowest ratio. This is a molecular
just for,
compound.
Like these, like, we just leave them right.
Yes, exactly. Yeah, because it's trichlorine, it is nona fluoride. Molecular compounds can be any ratio. Yeah. Yeah, but ionics have to be the smallest. You're right. Okay, what's the mass of that? 277.35. Will that go on top or bottom? Grams per mole of. So the moles have to go on the bottom, so it'll cancel. Okay, so 3 sig figs and then 5 sig figs. The answer would be 3 sig figs. So anybody get the answer? What'd you say, Lily? 1.42. Anybody else? 1.42 10 to the 4th grams, right? Can I squeeze grams in here? Sure. Okay. Got that? Okay, let's try this one. What is the mass in grams of 3 moles of magnesium chlorite? So, again, mass. When I see the word mass or grams, I'm thinking molar mass. Got to use molar mass. 3.00 moles. What's the formula for magnesium chlorite? Magnesium chlorite. Mg ClO2. Mg is 2 plus. Chlorite ClO2 negative. That's true. So how do I make it balance out? 2 chlorides, yes. Parentheses ClO2, parentheses 2. Okay, add that all up. And then tell me, will the mass go on top or the mass go on bottom on this one? So add it all up. Okay, so where's the mass? Where's the grams go? Where's the moles go on this one? Mass goes on top. What is the mass of magnesium chlorite? Anybody?
159.
No, the mass? 159.20, I guess I'll assume. That's the mass of a mole of magnesium chloride. Okay, so you multiply that out, and what'd you get? What'd you get, Marlies? Oh, get the answer? Okay. So what is it when you multiply it out? So how many sig figs should I have? 3. So what is it? 477? 478? Sounds good. Okay, let's try one the other way now. Let's take the moles. Oh, hey, Pierre, I wanted to ask you, do you have my exams? Can I go back in here real quick? How much time do you want to give them? Was 2 hours enough, or do you have to give them extra time?
I gave 2 people 10 extra minutes.
Okay. Perfect. Thank you.
Yeah, this one will be for the blue and the purple are down.
Okay, great.
Oh, this is
Oh, okay. Was there any problems or questions, or anybody have any
Yeah, they
confusion?
had questions, but I'm not sure they were legitimate questions. You gave them number of moles on a problem where you had, I think it was I2 plus BR2, give them IBR2 IBRs.
Okay.
And you only gave them the number of moles, and they wanted to know what's the volume so they can calculate the molarity so that they can.
Yeah. Yeah,
I didn't know what to answer to. I mean, I know the answer.
What did you say? What did you say to them?
I told them that they didn't need the volume.
Yeah, you're right. Okay.
But
Okay,
what
good.
I'm saying is that I didn't know if I should say that.
Okay. Oh, that's fine.
But I said
That
it.
might be said. Okay,
Okay.
that's fine. Thank you. Okay, let's try one the other way. How many moles are in 189 grams? Okay, grams. Ding, ding, ding. That's a mass. Got to use molar mass. Strontium phosphide. What's strontium phosphide? SR3P2. Good. So add up 3 strontiums, 2 phosphorus. Find the mass. Will the mass go on the bottom or the top this time? Will the grams go on the bottom or the top this time? Now I'm starting with grams. Let's go on the bottom this time. So what is the mass of 3 strontiums and a phosphorus? Anybody get it? 324.8. Probably, I'm going to say 80 then, because it probably had 2 decimals. Anybody else get that? That's the mass of a mole of SR3P2. So it must be a decimal something. So how many sig figs should I have? 3. So what is it? 0.582. Okay, sounds good. Okay, so let's put this whole thing together, because again, we can't actually work with moles in the lab. We can work with molecules and atoms. We can work with grams. And the way we get between those two is our new crossroads, the mole. So we can turn atoms into grams, and we can turn grams into atoms or molecules. So I've shown you 2 different tools in your chemistry tool belt here, and you have to know when to use which one. The first tool is Avogadro's number. So anytime you see atoms, molecules, you should think, Avogadro's number. The other one was molar mass. So I was showing you, whenever you see mass or grams, I got to use molar mass. So let's put it together and try if you could use both here. So, how many atoms? Okay, ding, 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 atoms. That makes me think Avogadro's number. I got to use Avogadro's number. Rn 54.6 grams. Grams. That makes me think mass, molar mass. I got to use molar mass. So I'm going to keep hitting this. It eventually will sink in here. So I'm starting with 54.6 grams of nickel. And I want to know how many atoms are in 54.6 grams. So I have 2 possible tools in my tool belt. I can use the molar mass tool, or I can use the Avogadro's number tool. Well, I'm starting with 54.6 grams. Grams is a mass, so whenever you use mass, what do you use? Molar mass. Molar mass. So find what's the molar mass of nickel. What is it? No, nickel. 58.69? Okay, will that go on top or bottom? 58.69. 5.69 grams on bottom is a mole, 1 mole of nickel. Okay, now I'm in moles of nickel, but I want to be in what? Atoms. Oh, atoms. How do I go from moles to particles? Avogadro's number. Okay, so where does that number go? On top or bottom? The moles goes on top, so Avogadro's number must go on, moles goes on bottom, so Avogadro's number goes on top. Yes, so 6.022 times 10 to the 23rd atoms is 1 mole of nickel. Okie dokie. Okay, does that make sense? Okay, well, we'll do a bunch more of these. So punch it in your calculator. 54.6, that's 3 sig figs. 58.69, that's 4. 6.022, that's 4. So the answer must have 3 sig figs. Okay, hit me with an answer there, somebody. Gonna have 3 sig figs, we know. 5.60 times 10 to the 23rd atoms. Okay, that's how many particles are in 54.6 grams. Okay? Let's try, why don't you try this one? So, okay, so just a little time out here. These really are word problems. I want to show you how to find those clues of what to do. How many formula units? Oh, formula unit. That should be setting off a bell in your head that says, that's a kind of particle. I'm going to have to use Avogadro's number. Rn, 6.12 kilograms. Oh, that is a mass. I'm going to have to use molar mass. You see that? So, start with what you know, which is 6.12 kilograms. What's the formula for lithium nitride? Li3N. The only extra little step here is what? Yeah, I'm in kilograms. I got to be in grams for the molar masses. So I got to take kilograms and turn that into grams. What's kilo mean? 10 to the third. Yeah, 1,000. So that go on top or bottom? Where's the kilo? On the bottom. So 10 to the third goes on the... So 1 kilogram is 10 to the third. Okay, now you can do everything as normal. So go on from there. Try the next part, see what you think. So what are you going to do next? You're going to use Avogadro's or molar mass next? I'm in grams, so I need to use a molar mass. Right, that's a mass, so I'm going to use molar mass. So add up your 3 lithiums, your nitrogen, punch it all in there. Question? You know what to do here? So we are, yes, you're right. So you need the grams. That's fine, that's right. You got this part.
Okay.
F you. So you're going to add up.
Oh, sorry. What
No, it's right. I'm just being funny.
Okay.
Okay. So I'm in grams. So when I'm in mass, I got to use molar mass. So you add up 3 lithiums, a nitrogen. It's like 30-something. What is it?
34.83.
So will that go on top or bottom? On bottom. So 34.83 grams on the bottom is a mole of, and I saw most of you were writing Li3N, but a few of you didn't. Write that Li3N, because here in a few seconds, it's going to bite you in the butt if you don't have that in there. So now I'm in moles, but I want to be in formula units. So moles to particles, Avogadro's number. Where's Avogadro's number go? Top or bottom? Yes, the mole has to go on the bottom, which means Avogadro's number must go on the top. And I guess I'll use the FU abbreviation here. So, now moles cancels. I'm left with how many formulas? Let me see. So we got 6.12, that's 3 sig figs. This is exact. This is 4. This is 4. So my answer must have 3. So what would it be? 1.06 10 to the 26th formula units. Yes, question.
Why isn't the 6.022
It's not exact. Well, it's not exact because there is actually more digits, and it could go out a whole lot more digits. Kind of like pi, it goes on a lot and a lot. It's only rounded off to 4. It hasn't been defined. I mean, it was. I mean, it is the number in 12 grams, but again, it could have been 6.022. I don't even know what it is. 6329, whatever. So we just rounded it off to 4. Yeah. Okay. Let's try this one. Let's do like 2 more. We'll have a little break here. I'm sure our brains are fried. And we'll come back. So, what is the mass in grams? Aha, mass. That makes me think molar mass of 3.05 to 10 to the 24th gold atoms. Aha, atoms. Avogadro's number. Okay, I'm telling you, you got to be able to pull out those little verbal clues. So, that's right. What I know here. I'm starting with 3.05 times 10 to the 25th atoms, gold atoms. So, what's the first thing I'm going to do? What's the first thing I'm going to do? Molar mass or Avogadro's number? I've got atoms, that's a kind of particles. So when I see atoms, I've got to use Avogadro's number. Will Avogadro's number go on top or bottom? Yes, I'm in particles, so it has to go on the bottom. So 1 mole of gold on top is 6.022 times 10 to the 23rd pieces of gold, which are called atoms, right? That's not going to work. Now I'm in moles, but I want to be in mass. How do I go from moles to mass? How do I go from moles to mass? How do I go from moles to mass? What do I use? Molar mass. Molar mass. Yes. So find the molar mass of gold. It's like 197 something. 196.97. Does that go on top or bottom? 196.97 grams per mole of gold. So mole of gold cancels. And now we're in mass, which is what we want. So 3 sig figs, 4 sig figs, 5 sig figs, must be 3. Okay, how many grams? 3 sig figs. How many grams? What'd you say, Lily? 9.98 times 10 to the 3rd grams. You agree with that? Awesome. Okay, your turn. You guys try D, then we'll have a little break. Come back and do some more. What is the mass in grams? Mass. Ding, ding, ding. My bell's going off. Molar mass. I know I got to use molar mass. Of 2.8 times 10 to the 19th formula units. Oh, ding, ding, ding. That's a kind of particle. I'm going to have to use Avogadro's number. of beryllium nitrate. Okay, try that out. Help each other out. See what you guys think here. Got so 2.8. Whoops, wrong number, wrong pin there. 2.8 times 10 to the 19th formula units. Oh, let me see what that is. What's beryllium nitrate? BE what? Right, good. So, if I'm in formula units, that's a kind of particle. So according to my little magical flow chart over here, what's the only thing you can do with particles? Avogadro's number, right? So will Avogadro's number go on top or bottom? Bottom. So 6.022 times 10 to the 23rd formula units per mole of, and again I'm writing what the mole is because that'll be important here after our break. So formula units goes bye-bye. Now I'm in moles, but I want to be in mass. Oh, moles to mass? Molar mass is right there in the name. Moles to mass, molar mass. So you added up the molar mass of that, and what is it? 133.03? Okay, that's the mass of a mole of beryllium nitrate. Awesome. Okay, so how many stick picks should I have? 2. So what is it? What'd you say, Aaron? 6.2 times 10 to the negative 3. Okay. Okay, let's take a little 10-minute break here. Let's come back at, what'll it be, about 5 after? Okay, come back at 5 after. Then we'll do a little more. Then we'll have our break, have our lecture, do a little more. Come back at 5 after. So we're going to talk about something called the mole-to-mole ratio now. Now, you know that when you write a formula, like H2O or something, that's the ratio of the atoms in that molecule. So H2O means there's 2 hydrogens and 1 oxygen, right? That's pretty simple. So for every 1 molecule of H2O, there's 2 hydrogen atoms, or there's 1 oxygen atom, right? Well, that same ratio also works for the moles. So if I have 1 mole of water, H2O, that means there's 2 moles of hydrogen in that 1 mole of water. Or there's 1 mole of oxygen in that 1 mole of water. So I could imagine writing a bunch of different conversion factors in that. 2 moles of hydrogen per 1 mole of water, 1 mole of oxygen per 1 mole of water, or 2 moles of hydrogen per 1 mole of oxygen. So that all just comes out of the formula, right? H2O, H2, 2 hydrogens, O, 1 oxygen. So that's a new way of doing a conversion. Because we'll find sometimes in chemistry or science or medicine, you don't really care what the entire molecule is. All you care is how much sodium is that patient getting out of the whole molecule? Or how much potassium are they getting? So there may be 3 potassiums in that 1 molecule, that formula unit. So they're getting 3 times. So this ratio is really important to us. So we're going to use this, what's called mole-to-mole ratio, whenever we're converting between 2 different substances. So let me show you an example here. How many nitrogen atoms are in 56.04 grams of dinitrogen tetrahydride? Okay, so I've been doing this. I'm going to keep doing this. I'm going to highlight all the little clues that are in this problem that tell you what to do. How many atoms? What does that tell you you're going to have to use? Avogadro's number. Are in 56.04 grams. What does grams mean you're going to have to use? Molar mass. Now the new clue we're seeing is this. Here I have nitrogen. Here I have dinitrogen tetrahydride. 2 different things, right? So whenever you see two different substances, we're going to use what's called this mole-to-mole ratio. So I can just tell I'm going to have to use three different things in this problem. Avogadro's number, molar mass, and this new mole-to-mole ratio. The question is, what order do I do it in? Well, let's just kind of start here and see if we can make sense of this. So 56.04 grams. What is dinitrogen tetrahydride? Dinitrogen tetrahydride. N2, dinitrogen tetrahydride. H4. Okay. Okay. I have mass. When you have mass, there's only one thing you can do. What is that? Molar mass. So let's add up 2 nitrogens, 4 hydrogens, 28, 32.06. That turns the mass into moles of, again, now it's really important that we write in what it is. So this is why. So I just use molar mass, right? Molar mass. Okay? So here is where I convert one substance into another substance in this mole stage. Because it's called the mole-to-mole ratio. So I want to turn moles of N2H4 into my goals, which is just moles of N. Are you with me? So this is where I do this. I want to turn N2H4 into N. So what's the relationship between moles of N2H4 and moles of just N? What's that ratio? Based on the formula N2H4, how many N's are there for every N2H4? There's 2 N's for every N2H4, right? So that's that mole to mole ratio. So that just comes right out of the formula, right? Everybody sees that? Right? See this 2 right here? It comes right out of that formula. There's 2 N's in every N2H4. Okay, now I'm in, let me cancel here. Now I'm in moles of N, but I want to be in what? So I'm in moles of N, but I want to be in atoms of N. How do I go from moles to atoms? Avogadro's number. Right. So 1 on the bottom, 6.022 times 10 to the 23rd atoms on top. Okay, so we have 3 tools in our tool belt. The only trick is knowing which tool do I use. If I see mass, grams, I know use molar mass. If I see particles like atoms, formula units, molecules, I use Avogadro's number. If I see 2 different things, I'm going to use this thing called the mole-to-mole ratio. So I worked this out, and what did I get? Let's see. 2.105 times 10 to the 24th atoms. Yeah, question. Oh, question.
Is that atoms of nitrogen?
Oh yeah, sure, that's fine too. Yeah, you can do atoms of nitrogen. That's fine too. Okay, so it just comes right out of the formula here. So there's 2 moles of nitrogen in every 1 mole of N2H4. If it was hydrogen, I would have said 4 to 1. As I was showing you on that previous slide, I was saying, so 1 H2O, there's 2 hydrogens per 1 H2O. There's 1 oxygen per 1 H2O. Now in this case, there's 2 nitrogens per 1 N2H4, or there's 4 hydrogens per 1 2H4. So it just comes right out of the formula there. It's just given to you in the formula. Okay. Oops, what happened there? Okay, so let's try one. How many chlorine atoms are in 39.2 grams of strontium chlorate? Okay, so this might get old, but I think it's helpful. Let's just read it again and figure out all the little hints. How many chlorine atoms? Atoms tells me I'm going to have to use Avogadro's number. Are in 39.2 grams. Grams tells me I'm going to have to use a mass, molar mass, right? And then, but now the new clue is the atoms are of chlorine, the grams are of strontium chlorate. So I have two different things. So two different things tells me I have to use this new thing, the mole to mole ratio. Okay, so let's try this out. So 39.2 grams. What's the formula of strontium chlorate? SR, parentheses, ClO3, these two. Okay, awesome. So, based off what I'm starting with, what's the first thing I have to do? Which of my tools am I going to use first? Molar mass, right? I've got a mass. So whenever you have a mass, all you can do is molar mass. That's all you can do. So add up a strontium, add up 2 chlorines, add up 6 oxygens, and tell me what you get. Or just stare out the window. What's the molar mass of strontium chlorate? Anybody get that yet? What is it? Anybody get it yet? 1 strontium, 2 chlorine, 6 oxygens. 254.52? Okay, that is the mass of a mole of strontium chlorate. So mass in the bottom, moles in the top. Okay. So when I'm in the moles, this is when I do the mole to mole ratio. So I want to relate moles of strontium chlorate to my goal, which is chlorine. So let's put strontium chlorate on the bottom. Run out of room there. And chlorine on the top. What's the relationship? How many chlorines are in strontium chlorate? 2 chlorines for every 1 strontium chlorate. Now, what if it had said oxygen atoms? What would I put in there? I would put 6, right? Because 2 times 3, there's 6 oxygens for every one of these. Yeah, but it's chlorine. Okay. Now I'm in moles of chlorine, but I want to be in atoms of chlorine. So, Avogadro's number, right? When you see atoms, oh, ding, ding, I need to use Avogadro's number. So that will go on top or bottom. Well, I'm in moles over here, so that means moles has to go on the bottom. So yes, Avogadro's number will have to go on top. And the smallest piece of a chlorine is called an atom. So chlorine atoms or atoms of chlorine. You can write chlorine in there if you want. So multiply that all out, and what'd you get? Anyone? Anyone? Bueller? .85 times 10 to the 23rd. I don't know anybody else. I didn't check it yet. Awesome. Okay. Now the next one's going to play with your brain a little bit, but that's why I just got to know the tools. There is no set pattern like, oh, it's always molar mass, and then molar ratio, and then Avogadro's number. No, you got to know what the tools. So what's it telling you? Oh, if it's mass, I use molar mass. If it's particles, I use Avogadro's number. It's just whatever it gives you, you know how to respond. So let's try this one. What is the mass in grams of a xenon hexafluoride sample containing 40.0 grams of fluorine. Okay, so let's break it down. Figure out all of our little clues here. What is the mass in grams? That tells me I have to use what? Molar mass. Of a xenon hexafluoride sample containing 40 grams. What does that tell me I have to use? Molar mass. And then I have two different things. I have xenon hexafluoride and I have fluorine. So that means I have to use that ratio, the mole to mole ratio. So this tells me I'm using molar mass twice and mole to mole ratio once, right? Nowhere in this problem does it ever mention the word atoms, molecules, formula units, anything to do with pieces, right? But I always have students just want to try to find a way to cram it in there and use it sometime. But there's no reason to, because it only gives you mass and it gives you mass. So let's try it out. So I'm starting with 40.0 grams of fluorine. Okay, so I've got mass of fluorine. What's the only thing I can do when I have mass? Molar mass, yes. So molar mass of fluorine, I think it's 19.00. So that will go on the bottom. And that will turn grams of fluorine into moles of fluorine. Okay, what's the next thing I'm going to do? I'm in moles. The ratio, the mole to mole ratio. So you got to be in moles to do moles to moles. So I want to turn moles of fluorine into moles of, what's the formula for xenon hexafluoride? XeF6. So, what's the ratio? What goes on top, what goes on bottom? What goes on top? 1 per 1 xenon has 6 fluorines, right? There's 6 fluorines in xenon hexafluoride. Okay, time out. Everybody sees that, right? Everybody sees why? Just comes right out of the formula. XeF6. There's 6 F's in that. Okay? So here's the point everybody starts to think, okay, well, I haven't used Avogadro's number yet. I must need to cram that in here somewhere. But you don't. You're in moles and you want to be in what? Mass. So moles to mass. What do we use? That was way too quiet. Moles to mass, what do we use? Molar mass. Yes. So don't try to cram a square peg in a round hole. If it say mass, I'm going to use molar mass. So let's find the molar mass of XeF6. So add up an Xe. Add up 6 fluorines. Okay, what's the molar mass of XeF6? 245.29. That's the mass of a mole of XeF6. Okay, so you multiply that all out. 3 sig figs, 4 sig figs. By the way, I should mention this ratio is a counting number, so that's exact. There's exactly 6 in there. It's not. That's exact. So 3, 4, exact, 5. So 3 is the fewest. So what is it? 8.61 times 10 to the 1? Oh, well, 86.1 in other words.
Yep.
Awesome. Good. Perfect. Okay, questions? Okay, your turn. Try C. Your turn. Try this one. break it down, figure out the clues. What's it telling you to do? I mean, it really does tell you once you know the patterns to look for. Let's work it out here, see what we got. Oops. So 2.03 times 10 to the 23rd copper atoms. So when you see atoms, what do you start thinking about? Avogadro's number, right? That's all you can do. So will that number go on top or bottom? Bottom. So that will turn atoms of copper into moles of copper. Put Cu there, why not? Okay. Now I'm in moles of copper, but I want to be in the end goal is mass in grams of copper 1 sulfate. So two different things, copper and copper 1 sulfate. So I got to use the mole to mole ratio. So I'm in moles of copper already, but I want to be in moles of what's copper 1 sulfate's formula? Cu2SO4. So what's the ratio? What goes on top, what goes on bottom? 1 to 2. Okay. Now I'm in moles of copper 1 sulfate, but I want to be in what? Mass. Moles to mass? Molar mass, right? Hopefully this is slowly sinking in here. So you add up 2 coppers, a sulfur, 4 oxygens, and what is that mass? 223.17 grams. Anybody else? Okay. Okay, so you multiply that out, and it should have, looks like 3 sig figs. So what is it? How many grams? I'm sorry? 37.6? Fabulous. Okay, questions? Now's the time. Okay, I got several little YouTube videos on this. I encourage you to watch them. That I put up on molar mass, on Avogadro's number, on the whole thing, on mole-to-mole ratios. I think those videos are pretty helpful just to watch them again and go back and revisit it. And then, of course, practice this stuff. Okay, I'm going to skip this one just because we're a little low on time. And now I'm going to do a different variation, basically the exact same thing we just did. But now instead of using the formula for the mole-to-mole ratio, we're going to use the balanced equation for the mole-to-mole ratio. Because we remember back we said a while back that this thing called the conservation of mass, that matter can either be created or destroyed. So whatever matter goes in, that same matter has to come out. So in an equation, the reason it's balanced is if 4 oxygens go in, 4 oxygens come out. So you don't make new elements. All you do is just rearrange them and find them new partners. So for example, if I put in butane and oxygen, well, that's carbons, hydrogens, and oxygens. I'm going to get out another variation of carbons, hydrogens, and oxygens. But the matter that went in equals the matter that came out. So 266 grams goes in, 266 grams comes out, right? Conservation of mass. Same thing with some of the elements, right? Which is why things are balanced. 4 carbons goes in, 4 carbons comes out, right? Whatever it is. So that's the conservation of mass. So this helps us now in equations because it's the same thing. The reason we have those balanced equations shows us that whatever goes in has to come out. So let me look here. So we call this whole thing, now when we're using equations, we call this a fancy Greek word called stoichiometry. Stoichiometry. So those balanced equations we were writing are basically like a recipe. A plus B gives you C plus D. So just like any kind of recipe where so many eggs and flours and whatever gives you so many cookies, right? So I happen to pull one up here. So this is like a balanced equation in a sense, where this ratio of reactants gives you this ratio of products. So, of course, if you change the ratio of reactants, well, you're going to change how many products you get out too, right? So, for example, in a recipe, if I were to suddenly change the ratios, let's say I use twice the salt and half the eggs, I would not still get out 60 cookies. Or I might, but they wouldn't be cookies you'd probably want to eat, right? They'd be disgusting cookies. But the same thing in chemistry. If I change the ratio and it's balanced at 2 to 3 and I make it 4 to 3, well, now I won't get the same ratio of products. It's going to change the ratio of what I get out. So we use this all the time in chemistry, engineering, medicine, things like that, because it helps us then to predict exactly how much I have to use of the reactants in order to get out exactly so many products. And then we're not wasting extra reactants just guessing. So, for example, let's look at this one. Let's say you're working in a factory. You're trying to make nitrogen dioxide. And the process you're using, according to the balanced equation, is 2 nitrogen monoxides plus 1 oxygen produces 2 nitrogen dioxides. Well, if I want to produce 2 nitrogen dioxides, well, I'm going to use exactly 2 NOs if I can, right? I'm not going to use 47 NOs and just use a bunch of extra, right? I'm going to use whatever the exact ratio is. Else you're just wasting chemicals, which costs money, so you're just wasting money, right? So you're going to use the exact ratio. So this tells me for every 2 NOs, I need 1 O2. Or it tells me for every 2 NOs, I make 2 NO2s, right? All kinds of ratios come out of that. So that is the ratio of the individual molecules, but it's also the ratio in moles. So this could be 2 moles of NO needs 1 mole of O2 to make 2 moles of NO2. So it works for individual pieces, and again, it works for moles. Just like the mass works for individual pieces, and it works for moles. So this ratio is super handy. So let me show you one here. So I could write that. So that's another way of getting that mole to mole ratio out. I could use the the equation. 2 to 1, or 2 to 2, or 1 to 2. I can get lots of ratios out of that formula the exact same way. So let's show you another one here. Let's look at this one. N2 plus O2 goes to 2NO. So that tells me for every 1 mole of nitrogen that I react, I've got to have how many moles of oxygen? Nope. For every 1 mole of nitrogen, I got to have how many moles of oxygen? 1 mole of oxygen. It's 1 to 1. 1 N2 plus 1 O2. And for every 1 mole of nitrogen I react, I'm going to get out how many moles of NO? 2, right? See that? 1 to 2. For every 1 mole of oxygen, I'm going to get out how much NO? 2, right? So you can see all these ratios come right out of that balanced equation, right? 1 to 1, 1 to 2, 2 to 1, 1 to 2, 2 to 1. We get out all kinds of mole to mole ratios right out of the balanced equation. So it's just another way, again, of doing that mole to mole ratio, right? It could be out of the formula, or it could be out of the balanced equation. So let me just show you. Let's do a real quick, easy one. How many moles of oxygen would I need to react with 2.25 moles of nitrogen? Well, if we're going to write up as a little calculation, we would write up something like this. If I can get this stupid thing to lift up. Here we go. 2.25 moles of nitrogen. So that's this stuff. I want to know how much of this stuff will I need? Oxygen. So, what's the relationship between moles of nitrogen, that was very crappy, and moles of oxygen? What's the relationship between the two? Not 1 to 1, right? For every 1 nitrogen, I need 1 oxygen, right? Oh, so that means I would need how many moles of oxygen? Same thing, 2.25, right? So again, this mole to mole ratio just comes right out of the balanced chemical equation. So everybody sees where that 1 to 1 came from, right? It's just the coefficients on the equation. If it was nitrogen to NO, it would have been 1 to 2. Right? Okay. Okay, let's look here. 2.25. Okay, let's look at this one. Let's say you're going to burn some gasoline in your car. Gasoline is primarily octane, which is why fuel pumps then always have an octane rating on the gas. You know, it's 93 octane rating or whatever. Well, what's octa mean? 8. So octane is a hydrocarbon that has 8 carbons, C8, H18. So when you burn hydrocarbons, we know from the last lecture a couple weeks ago, that's a combustion reaction. So hydrocarbons plus oxygen always give out carbon dioxide and water. Okay, so let's just look at this one. So the balanced equation is 2 octanes plus 25 oxygens produces 16 carbon dioxides and 18 waters. Okay, so let's look here. How many moles of oxygen are needed to burn 1.25 moles of octane, C8H18? So I have moles of octane, but I want moles of oxygen. What's the ratio between oxygen and octane?
2 to 25.
2. Oh, crap. What did you just do that for? Sorry, I don't know what happened there. 2 to 25, right? Right there. Two moles octane to 25 moles O2. So multiply that out, and how many moles of oxygen would you need? Anybody?
15.6.
15 point what? 6?
65, but rounding is
0.65?
0.625.
Oh,
But
6, okay.
I would say negative figures are 0.6.
Sounds good. Okay. How about this one? How many moles of octane would I need to make 5 moles of carbon dioxide? So you're working in your factory, you got to produce some carbon dioxide. You don't want to waste any octane, so you want to use the exact amount of octane you need. So if you've got 5 moles of carbon dioxide, how much octane will I have to use? So we're going to relate moles of carbon dioxide to moles of octane. Where do I find that relationship? Right there on the balanced equation. So how many octanes? How many moles of octane do I put on top? 2, right? How many moles of carbon dioxide do I put on bottom?
16.
So what's the answer? Something small.
0.65.
Sounds good. 0.625 moles of octane. Point 6. Okay. Well, I can also, you can imagine though, wait, back up. So you can imagine though, of course in the lab again, we don't do things in moles, right? We weigh them out like in grams and things. Well, fortunately you know how to turn all those moles into mass. Just use the molar mass for these things, right? So let me just skip ahead here because I think we got this now. We are experts at molar mass. Let's try this one. How many grams of oxygen, now grams, molar mass, are needed to burn 10.0 grams of octane? Oh, grams, molar mass. So again, if I was reading this problem, I would say mass in grams. Oh, that's molar mass. 10 grams of octane. Oh, molar mass again. But I have oxygen and octane, two different things. Mole to mole ratio. So just reading it, I know I got to use 2 molar masses and I got to use 1 mole to mole ratio. This will be our last little thing here before we have a little break before lecture. So 10.0 grams C8H18. Okay, what's the only thing you can do when you have mass? You should all be screaming at me, molar mass! Okay, so find the molar mass of C8H18. So 8 and 12 is 96, and 18 is 114.26. Double check that, but I think that's right. Okay, so I'm in moles of octane, but I want to be in what? What's my goal? Not octane. I want to turn the octane into what? Oxygen. So how do I relate octane to oxygen? Yes, so what is it? So what do I put on top? 25 oxygens. How many octanes on bottom? 2, right? 25 and 2. You with me? Okay. Pretty much similar to what we were just doing. Now I'm in moles of oxygen, but I want to be in mass of oxygen. So what do? Moles to mass. Molar mass, right? Molar mass again. So what's the molar mass of oxygen? Yeah, add up 2 oxygens. Each one's 16, so 2 of them is 32. So 3 sig figs, 5 sig figs, exact, and 4 sig figs. Going to be 3 is the fewest. So what's the answer? Anybody? $17.0? $70.0. Anybody else get that? No?
I got 35. You missed the 2 on the bottom.
I think you didn't divide by 2. 35.0?
Yeah.
Okay, so basically the same as what we were just doing, but now so this is all the same. The only thing different is this right here. We find the mole-to-mole ratio now out of the equation instead of out of the formula, but it's the same thing. So it's really just different variations on the same thing I've been doing for 3 hours. So it's always either Avogadro's number, molar mass, or mole-to-mole ratio. And the mole-to-mole ratio can either come out of the formula or the equation. That's all we've done for 3 hours. 3 things. Avogadro's number, molar mass, mole-to-mole ratio. Yeah.
Will you be nice to us in the test? Because this is a lot.
I'll be nice on the test. well, you have a week, so you have almost a week.
When's it on Tuesday?
Oh,
Monday.
Oh, Monday, yeah.
so yeah, you have 5, 6 days. Yeah. So practice hard. Come see me. Go to FLS. Go to Tutorial Center. Start early. Okay, so we're gonna meet over there at class, and we'll finish the chapter up. And then if we don't, and if we have time, we'll do some more of that ionic, some of that naming worksheet. So bring that naming worksheet with you, the tan one I gave you. Did anybody not get one of these? If not, grab one real quick. Oh yes, having our quiz. I'm sorry, grab that. Yes, having our. No. Yeah, no Scantron for the quiz. Okay, so I'll see you in a few minutes.